So in Chapter 6, we're going to start looking at rational expressions, which is basically just fractions of polynomials. So really, if you're expecting anything new in this chapter, there's not going to be much. The first idea we're going to talk about is different, but all the rest of them, adding, subtracting, multiplying, dividing, all of that is going to be the exact same as whenever we're dealing with fractions back in Chapter 1. So right now, I would encourage you guys to go back to 1.2, review all those rules, make sure you can do them in your sleep almost. Because whenever we get here, I'll be able to show you a couple examples, but unless you already have the rules memorized, it's not going to do you a lot of good. So make sure to practice it first, then keep going with this stuff. Now, just to give you guys kind of an idea of what we're going to be looking at, these are rational expressions. So I've got 3 different ones listed out here. And the reason I put in this guy is hopefully to prove or to help you guys really realize that it could be just normal fractions. So all the rules that we'll talk about fit perfectly for real number fractions. Now they could be something along this line. Probably most of the problems are going to fit into this level of complexity. Some of them could be really complex. We will probably not be dealing with those, but it exists. So basically any polynomial on top and any polynomial on the bottom makes a rational expression. Now the first idea that we have to do is figuring out where these are defined. So as soon as you make a fraction with variables, you have the possibility of getting a 0 in the denominator, which you can't have. You can't divide by 0. So you have to make sure to avoid those. So that's what we call having an undefined expression. Basically, you look at the denominator of your equation or your expression. You make sure that it's not equal to 0, so you take out those values, and everything that's left are going to be the good values. I'm kind of skipping over words that I shouldn't be using at this stage, namely domain. Technically, we're trying to find the domain of this expression, which that's more in college algebra land there, but that's what we're going to be doing. Okay, so if you take something specific, like let's try and find the values that we have to avoid in part A here, that equation. I don't care at all about the top. I want to look at the bottom only because this is entirely concerned with having a 0 in the denominator. So I take whatever the bottom piece is, I set it not equal to 0, and then I solve that equation, whatever it happens to be. Now, the book and I are going to differ a little bit. I like to put the not equal to symbol to remind myself that these are the bad values. You could just say x plus 2 equals 0 and solve it, you get the same thing. Okay, so just for me, I like reminding myself that it's not equal to this. So whenever I solve it, I see that x cannot be equal to -2, which tells me that I have to avoid that value. So technically, that's your answer. You cannot have -2. All the other numbers are good. So that's the only thing we have to pull out. You could write it a couple different ways. You could say that maybe we have to avoid x equals -2. Or whatever you can. Just kind of be creative about it if you want. But as long as you're telling me that -2 is the bad number, the only thing we cannot have. So whenever you get to parts B, C, and D, and the problems get a little bit more complicated, it's the same idea. The complex part comes in with being able to solve the equation you set up. So in part B, I should know that we have to set up this equation and solve it. Well, to do this, you have to remember how to solve by factoring, which we covered in the last chapter. So I told you it was going to carry over. Here it is right away. You have to be able to factor this apart. So thinking of numbers that multiply to -12 and add to +1. Once you figure out what they are, you know how it factors. Once you have it factored, you know that you can set each one of the factors equal to 0. Or in this case, we're trying to show what values to avoid, so not equal to 0, same difference. And figuring out that in this case, there are 2 values that you have to avoid. X cannot be 3, x cannot be -4. Alright, so same type of game whenever we get to part C. Take the denominator, still don't care about the top. I'm not worried about it at all at this point. I'm just trying to figure out what values to avoid. That will always come from the denominator. So absolutely no work dealing with the top of it so far. Think about how you're going to factor this one. Well, this is an AC method problem. You have to take the A value times the C value So you're not going to get away from any of the factoring methods we talked about. You're going to have to remember them all, and you have to be really quick on it. Because these problems, you have to, at least from an instructor viewpoint, we try and go through the factoring really quickly so that you can get to the actual rational expression stuff. So hopefully by now this is fast, easy, I'm hoping. I'm dealing with limited board space here, so once you get to that stage, you know that you have 4 terms. You would set down and group them, and you should get the following factors. 3q minus 2, 2q plus 1, not equal to 0. I freely admit I'm skipping a few steps there, okay? So you guys go through the grouping. I've covered plenty of those examples. Make sure that you can get to these 2 factors so that we arrive at the same answer, saying that q cannot be equal to 2/3 and q cannot be equal to -1/2. All right, taking each one of those factors, setting them not equal to 0, solving, should get those 2 answers. Okay, and then part D, I know it looks more complicated, but it should actually work a little bit easier because the factoring should be easy. If you recognize the difference of 2 squares, you know that this one's going to pull apart as a minus 3, a plus 3, not equal to 0, which means I've got 2 values to avoid here. And the same thing with a squared minus 25. That should factor into a minus 5, a plus 5, still not equal to 0, which means you set each one of those factors not equal to 0, and you get 2 more numbers that you can't have. So for part D, there are a total of 4 numbers that you would have to avoid. So in each of these cases, each of these examples, I've listed out the values you cannot have, the values you have to avoid to keep everything being defined. So besides, take this one, any number besides 3, -3, 5, and -5, anything else is going to be fine. You can plug it in, which is where I get the second part of that example. So if it makes sense having to avoid values, you can see that sometimes we might want to list the values that you can have, and that would be called the domain. The list of values that you can have. To get this, you have to start by finding the values you cannot have. And then you just, take those out, you make a list of everything that's left over. So I'm going to go through parts A, B, C, and D again, except this time I'm going to be listing the domain for each one. So the domain of part A. Well, if you remember, we said that it could not be -2, but that means that everything else is going to be fine. We haven't talked about interval notation, which is how we're actually going to be listing this out. So one way that I have of doing this is going back to the real number line. That's how we did it for inequalities, and it's how we can do it now. So if I want to take out -2, I know that means you have to have an open circle, because an open circle does not have that value. It's like you took out that value. But you have everything on both sides, because that was the only bad value. So that is one way of listing out the domain. Another way, interval notation, like I just said, is doing the same type of thing, but it's doing it with numbers and parentheses and brackets. So what you need to get used to is that a parenthesis means the same thing as an open circle. A bracket will mean the same thing as a closed circle. And otherwise, you're just going to be listing the different x values that it goes between. So if I'm trying to list out this thing here, I've got the x values on the left side, I've got the x values on the right side, and I need to list them both out. It starts at -infinity. So if you think about this arrow goes all the way to the left, it's -infinity, up to -2. That's the place where we have this break. So we have to skip over that number. It picks up again right after -2. And the arrow says it keeps going that way, so it keeps going to +infinity. So This is one way of giving the answer to the domain. This is the other way. And for this class, I'm perfectly happy if you give me this answer. College algebra will expect you to do interval notation though, so it's worthwhile getting used to this method. By the way, this little U symbol here is a union, which tells me I'm linking those two pieces together. So this is all one answer is what it means. All right, more practice with it. Let's talk about part B. So from over there, you remember part B said you could not have 3 or -4. Cannot have 3 or -4, but you could have all the values in between. That means you need open circles here and marking all the values in between them, like so. So that would be the domain. Another way of listing that would be an interval notation where you start at -infinity, because that's where my arrow or my line starts, going until you have your first problem, skipping over that problem point. You have to capture everything in between the -4 and the 3 as well, so that's why I have this portion to correspond to that value. And then you've got everything from 3 on up. Alright, so that one of these two for part B, that would list out the domain. Part C had the exact same thing. We could not have 2/3 and -1/2. So I know the numbers are different, but the idea is exactly the same. You cannot have this, you cannot have this, but all the other numbers are fine. So, picture-wise, we're looking at it like that. Interval notation-wise, we're starting at -infinity, going up to the first problem, skipping over it, getting all the numbers that might happen in between them, and then everything that would happen after that number. We haven't used brackets yet because we haven't been equal to any number really, but that could happen eventually. You'll probably see that in college algebra, not for this class, but remember brackets are a possibility. Okay, so one of those two answers, and the last one here, we're going to squeeze in part D. There were 4 values I had to avoid for this one, so it's going to take a little bit more writing. Concepts are not any different. Nothing has changed. You're just taking out more points. So whenever you think about the values you could not have, those 4 right there, everything in between is good. So whenever you list them out in interval notation, it starts with -infinity up to -5. Goes from -5 to -3. Goes from -3 to +3, and then continues from 3 up to 5, until finally, and I even ran out of room there, we go from 5 all the way up. Okay, so it can be a little bit messy to write, but unfortunately that's what it is. So there you go, talking about the undefined parts of rational expressions. Everything from here on out in the rest of chapter 6 should be just like the fractions we've talked about. So we're going to go through simplifying, multiplying, dividing, adding, subtracting, and then at the very end of it we'll get another new concept called complex fractions.